Okay, so for 5.2, we're going to talk about perpendicular and angle bisector. So first of all, a perpendicular bisector is going to be a line, segment, or ray. Line, segment, or ray that is perpendicular to a side at its midpoint. To a side at its midpoint. So let's take in the example below here side AB. Okay, I'm going to make its midpoint right here at x. So if that's its midpoint, I know that AX is going to be congruent to XB. Okay, so I'm going to make it a ray going straight up like so, and I'll put Y right there. So now ray XY, if I say that this here is a 90-degree angle, ray XY is going to be the perpendicular bisector of side AB. Okay, so here's what we can get from that. The perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. So here's point P. It's on the perpendicular bisector here. So PM is if PM is perpendicular to AB, here's PM, perpendicular to AB, so I put a little 90-degree angle sign, and MA equals MB, then I can say that PA is going to be congruent to PB. Okay? And the converse is also true. Whereas if I tell you that PA is congruent to PB, then I can draw the conclusion that PM is a perpendicular bisector with AB. And so MA and MB are going to be congruent. So what that looks like in practice is here I have a perpendicular bisector. Okay, so I know that PA and PB are equal. So 4x plus 6 equals 2x plus 22. Subtract 2x, subtract 2x. 2x plus 6 equals 22. Subtract 6, 2x equals 16, and divide by 2, and x equals 8. I can do the same thing over here. So now I can see here that this is a perpendicular bisector. These two, PA and PB, are congruent, so therefore I know it's a perpendicular bisector, so I can say that MA is congruent to MB. So I'm going to write 1/2 x plus 4. Excuse me. 1/2 x plus 4 equals 3/2x minus 6. So just like I did over here, I'm going to start by subtracting 1/2 x from both sides. And when I do that, I get 4 equals just x minus 6. So real quickly, just to kind of go over how to subtract fractions, if I have 3/2 minus 1/2, what I did in my head was I found a common denominator. And then you just add or subtract the top depending on the operation. So here I'm subtracting, so 3 minus 1 was 2. 2/2 simplifies to 1. So that's where I get my 1x from. So I'm going to add 6 to both sides. And so 10 equals x. Now, the distance between a point and a line is the length of a perpendicular segment drawn from a line to a point. So here, the distance would be from P to M is 5. Here, you can see that P is not form, this point P and the line to M does not form a right angle, right? It either forms an acute angle or an obtuse angle, depending on which side you're looking at it from. Okay? Now, if it forms a right angle, then we know that that's the distance. It's kind of like in a triangle. If I gave you a right triangle and I said that this is 3, that's 4, that's 5, you would tell me that the height is 4. You wouldn't tell me that the height is 5. And so, same idea. Our distance is going to be from a perpendicular bisector, or a perpendicular segment, to a point on the line. So a point the same distance as two lines is equidistant to those lines. So a park director wants to build a t-shirt stand equidistant from the roller coaster and the spaceship chute. What are the possible locations of the stand? So first I'm going to connect R and S. So I'm looking for a place to put my t-shirt stand that's the same distance from R as it is to S. It can't be M because that's much closer to S than it is to R. And it can't be at the paddle boat station because P is much closer to R than it is to S. So obviously I could put it right here. If I made that the midpoint, then this and this are the same, so this t-shirt stand would be the same distance to both R and S. It could also be right here, it could be here, it could be here, as long as it's anywhere that's on the perpendicular bisector. So here, it's equidistant. As long as that's a perpendicular bisector, this point is equidistant to both. It could also be here, where this distance, again, is the same as this. It could be here. So it could be any point that's on the perpendicular bisector. So it could be any of these points also. Okay, because any point that's on a perpendicular bisector is going to be equidistant to the two endpoints of that line that's perpendicular to. Now we're going to talk about angle bisectors. So an angle bisector of a triangle is a segment or ray that bisects one of the angles of the triangle. So here's angle C. I'm going to bisect it. Put this at D. So when I bisect it, what I'm doing is I'm cutting the angle in half. So ray CD is the bisector of angle C. And the angle bisector theorem says this. If a point is on the bisector, so here's ray QS, it's bisecting angle PQR. So if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. So in this case here, if QS is here, it's cutting this angle in half, and S is on the bisector, this point is going to be equidistant to P and R, so SP would equal SR. And the converse is also true. If these two lengths are the same, then I know that this must be a perpendicular bisector. So what that looks like in practice, here's our theorem, our angle bisector theorem. So I have an angle bisector and a point that's on the bisector. So I know that 7x equals 2x plus 30. Subtract 2x, 5x equals 30, and so x equals 6. You divide both sides by 5. Here, I have the converse of that. I have a point, and it's equidistant, because they're both, it's from S to P is 27, and from S to R is 27, so I know that this has to be an angle bisector, and an angle bisector cuts an angle in half, so these two angles are congruent. So 4x plus 23 equals 7x minus 28. Subtract 4x from both sides, and 23 equals 3x minus 28. Add 28 to both sides, and 51 equals 3x. Divide both sides by 3, and x equals 17. For the last part, I'm going to zoom out a little bit so we can see this just a little bit better.